of bread, imagine taking it into two, and then take it again, and point will it know. Theory number 1. Over 2,000 years after Democritus, John Dalton came up with the first scientific atomic experiment. In his experiment, he was able to state that all substances are made up of atoms, and that they can't be destroyed, divided, nor created, as atoms are indestructible and indivisible. Theory number 2. 100 years later, Joseph John Thomson came up with the notion that atoms are not just small spheres which makes up objects, but it has charge embedded somewhere within it. The atoms consist of positive charges and negative charges spread evenly throughout the atoms, which makes it electrically neutral. His model later is known as the plum pudding model, and it changed the way humans view atoms. He was also able to measure the ratio between the atom's charge and mass, 1.588 times 10 to the power of 11 coulombs per kilogram. This ratio was later succeeded by Robert Andrews Millikan with an experiment to measure the charge and mass of electrons. Number 3. Several years later, Ernest Rutherford experimented on a gold foil by shooting the foil with particles and found out that not all of the particles that went through the foil. However, most of the particles did. He then concludes that the foil is made up of mostly empty space from the electrons, which allows the particles to pass through, and there are nuclei of concentrated positively charged particles which cause the deflections. With the positively charged particles concentrated in the middle, its mass is also concentrated towards the center, creating a pull for the electrons which creates centripetal force. The pulling forces of both the electrons and the nucleus is equal to the centripetal force, therefore electrons travel in a fixed path. Mathematically, it is put as the constant multiplied by the square product of its energy over its squared radius is equals to its mass multiplied by its squared velocity over its radius. Hence, the magnitude of the kinetic, potential, and total energy of the electrons are expressed as so, with its dielectrical constant 9 times 10 to the power of 9 Newton meters squared per coulomb squared. However, if these electrons moved, which it emits energy doing, at one point, the electrons will run out of energy and collapse to its center. If all atoms are like this, every atom will be very unstable and thus would not exist. Number 4. In the matter of 2 years, Niels Bohr came up with the idea of shells. He stated that electrons circle the nucleus in specific allowed orbits, he referred to as the letters K, L, M, and N. The further down the list, the higher its energy. This is called stationary orbit. The electrons encircle the nucleus like planets encircle the sun. However, these electrons do not absorb or emit energy. It has angular momentum, expressed mathematically as the mass times the velocity of the electrons multiplied by the radius equals to its primary quantum number times Planck's constant over 2 pi. Each of the shells has its own energy level. If an electron goes from the inner orbit to the outer, it will absorb photons, and if it goes the other way, it will release photons. From Bohr's first postulate, the radius of the orbit is measured by so. And from the second postulate, the magnitude of electron energy in each shell is so. When an electron shifts from orbit B to A, there will be a photon emission as big as, with R as the Rydberg's constant, 1.097 times 10 to the power of 7 per meter. Each of the orbits of where it originates from and is going to will correspond to specific rows. Let us test ourselves now. How much energy is released when an electron from the fourth to the second energy level inside of a hydrogen atom shifts? Here is the answer. Though Bohr's theory and calculations are sophisticated, it has flaws too. The orbits of electrons are not just circles, but very complex pathways.
Further on, his model somewhat only is ideal to count hydrogen atoms, but not atoms with more electrons. His calculation goes obsolete. His theory also failed to explain the effects of magnetic fields to the atomic spectrum, and could also not explain chemical incidents well. The theories of atoms has went through a long journey throughout human history, and it is still bound to change again. But until then, we are lucky to have understood about atoms this far.